if you're willing to do science, you want to become a theoretical physicist or you want to become a scientist, then you should be clearly aware about your objective. Whether are you looking for money, you want to become a star, you want to add to your resume or your CV that you're a scientist, or you want to earn a lot of money. Well, if you're looking for that, then I would say don't do science. If you want to become a theoretical physicist, mathematician, or a scientist, then you need to do something which will come as a good to the society. The reason is that at the end of your career, you really feel good. Now, these are not my words, these are the words as told by François Barre Sinosi. She is a Nobel Prize winner, and she was the first to detect what is called HIV for the disease of AIDS. So it was the words of François Barre Sinosi that if you're really willing to do science, if you're really willing to become a mathematician, if you want to become something related to science and physics, then don't do it for money, but do it something which will come eventually good for the society. Quantum field theory is definitely one of the branches of science in modern physics, which requires a lot of mathematics, lot of research, and lot of hard work. And if you're looking in order to do well in quantum field theory, you should think that how you can teach and how this quantum field theory will come something use to the society. Now, having told all those things, let us welcome you back to the lecture. And today's lecture would be basically on what I say, lecture number 5, which would eventually speak on quantum field theory. And the basic idea of this lecture is to understand and clearly be aware about what is called a Lagrangian. Now, in this lecture, I have already done 4 lectures in terms of 1, 2, 3, and 4 for all the quantum field theory part. And whenever we go for quantum field theory, the first thing that comes to our mind is that why do we need to understand a Lagrangian? So today's video would be primarily to understand that why do we need Lagrangian, which is a very, very important concept. And once we understand that a Lagrangian is an absolute first step in understanding the mathematics of quantum field theory, then we can even then go far beyond the Lagrangian, and then we can find out something which is called a Lagrangian density. We can find which is called a Hamiltonian density, and so on. So today's video, I would like to explore the mathematics of Lagrangian in quantum field theory. But before that, what we need to understand is this, that why do we need at all a Lagrangian? Now, here are some quick points which will make you understand that the real need of the Lagrangian. Now, you see, the slide tells that Lagrangian actually plays a very, very important role in quantum field theory because it provides a powerful tool for describing and analyzing the behavior of quantum particles. Now, here, let me take a pause and make you understand that if you're not being able to understand the Lagrangian of the classical physics, then taking it forward and making you understand about the Lagrangian density or whatever it is in quantum field theory, things will become very difficult. So in particularly, we need to understand, first of all, that why do we need a Lagrangian? So first, you see, it is something which is called a covariance and relativistic in nature. Now, when we say that it is covariance and relativistic in nature, what do I mean by that? So what I'm trying to tell is that the Lagrangian formulation of quantum field theory is inherently covariant under Lorentz transformation, which means that it is well suited to describe the behavior of particles and fields in special theory of relativity. Now, you see that the basic idea is that when we started with quantum field theory, we found that quantum field theory is going hand in hand with special theory of relativity. So if quantum field theory is first going in hand with special theory of relativity, then we need to first understand that why Lagrangian is related to special theory of relativity. So the first thing that here you need to understand is that the formulation of the covariance principle. That means it inherently is covariant under Lorentz transformation, which Newtonian mechanics or the Newton's laws of motions were not inherently, I would say, Lorentz covariant. So because Lorentz transformation is the underpinning idea behind the relativity, I would say special relativity, hence the covariance has to be in terms of relativistic nature. This is point number one. Now, the second thing that you can see over here is what is called the unified framework. Now, when we do Lagrangian formalism, it actually provides a unified framework for describing both classical and quantum systems. That means it allows the physicist, or you can say the mathematician, to seamlessly transit or seamlessly do the transition between the classical and the quantum regimes. So it makes it a versatile tool for analyzing a wide range of physical phenomena. So here you can see that first we started with special theory of relativity because Lorentz transformation is in covariance with quantum field theory. So definitely the Lagrangian is in hand or covariant with special theory of relativity. Now, Newtonian mechanics is not covariant with special theory of relativity. Hence, obviously, classical mechanics is not going hand in hand with special theory of relativity. Second, as I told you that, as you see, that it is a unified framework. That means that it actually is seamless transition from classical to quantum realm. The third thing which you can see is the canonical quantization. I hope you understand the worm. What do we mean by canonical quantization? So it is the quantization of the electromagnetic of classical fields. So the Lagrangian actually helps in a very systematic canonical quantization, which is the process of promoting classical fields to quantum fields. And this leads to the creation of annihilation operators that actually describes the quantized excitation of the field. The creation and the destruction operator, which I have shown you in the earlier live classes, it is actually possible because of the canonical quantization. So the Lagrangian formalism naturally leads to commutation relations and the quantization of fields and enables the description of particles in terms of the quantum text. Also, we will soon see in today's video that deriving the equations of motion, that means the Lagrangian is actually used to derive the equations of motions in the fields of quantum field theory. And we will see that how Newton's laws of motions are going hand in hand with Euler-Lagrange, from this to that, how we can transfer. So this is particularly, and we have something more. So it actually tells that some symmetries and conservation laws, because the Lagrangian formulation highlights the different symmetries, like Noether's theorem allows us to connect the symmetries of the Lagrangian with conserved quantities. So the symmetries of a quantum field theory, which are actually very crucial for understanding the conservation laws and the behavior of particles, this is actually done using the Lagrangian. Apart from that, the path integral formulation, which is the Feynman's path integral formulation, it is introduced by Richard Feynman. This is a central component of quantum field theory. So a path integral formulation approach actually provides a powerful tool for calculating quantum amplitudes and probabilities by summing up all the possible paths or field configuration, taking into account those small quantum fluctuations. So the path integral will take the entire history of the trajectory. It will take the entire path, and that is how it is being done through Lagrangian. Remember, the Newtonian mechanics, it is only possible to pick up the discrete parts, and it is not possible to get the entire history of the particle. So we need to come to Lagrangian. So why I am telling you all this is because once you understand the real need of the Lagrangian, then only the mathematics will become useful, and then only you will see that from Lagrangian how we are moving to Lagrangian density, and what is the problem of classical Lagrangian that gets extended to Lagrangian density. So you see Noether's theorem, actually, because it speaks of symmetries, the Lagrangian is connected to Noether's theorem, which relates symmetries of the Lagrangian to conserve quantities in the physical system. So the theorem actually provides a tool for understanding the conservation of energy and momentum, angular momentum, etc. And I have already done a very detailed video on Noether's theorem. It is there on my channel, Physics for Students. You can see how Noether's theorem and symmetries save general theory of relativity and how Lagrangian is actually related to Noether's theorem. So the symmetries actually plays a very, very important and a vital role. Also, it has got consistency and predictive power. Now, this is important because the Lagrangian formulation of the quantum field theory provides a consistent and unified framework in order to describe a wide range of particles and interactions, including quantum electrodynamics as well as quantum chromodynamics. Yes, this unified formulation is actually possible due to Lagrangian, because once we move from QED to QCD, which is the quantum chromodynamics, we will see how this Lagrangian gets extended over there. So this is also very important, that it provides a consistency and predictive power. Apart from that, I think that what we can say, renormalization, which is again a very, very important factor over here, which I have mentioned, because we have dealt with renormalization, right, in the earlier lectures also. So the Lagrangian is essential for renormalization because it produces a variety of infinities. And if you go to my lecture number, this is 5, 4 or 3, you can see, I will summarize all those lectures, don't worry. So 4 and 3, you will see that what happens is that this renormalization actually helps to reduce these infinities to a finite size. Not only that, I have also shown that how Schrodinger's equation is unable to describe what is called spontaneous emission, because Schrodinger equation is very time dependent, and spontaneous emission, once it goes forward, it keeps on going. So taken all these things together, we can find out that why Lagrangian is very important, and why right at the beginning of quantum field theory, we start only with Lagrangian and then take it forward. So now what I will like to tell you is that, can we see the Lagrangian in terms of a easy mathematical formulation? How does it helps? How does it takes it forward? So I remove this from the screen, and I would like to add something, which is I'm going to show simple mathematical calculations, because until we understand the Lagrangian, again, moving forward with the next part, that is the Lagrangian density, would be very difficult. So for the time being, what I'm going to do is that I'm going to consider, I would say, a dynamical variable. Say, for example, I consider a dynamical variable, which would be something which is this one. I will just put it across in the Zide board so that it is easily visible to you. Just a second. Okay, okay, fine. So I would like to put forward like this. I would put the Lagrangian formalism. First, I would like to put the single dynamical variable as something like, I'm so sorry, it should be Qt. Let me just try it. Just a second. Yeah. So it would be Qt. Okay. So what I'm trying to do over here is that I'm taking the dynamical variable Qt, for example, of a position of a particle, and I'm taking it in a one-dimensional motion. So if I kind of take a trajectory, say something like this, and I'm taking a trajectory like this. So what I'm going to do is that, let me write it fresh for you. So I write it as Qt, and this goes under braces, right? So I'm taking a kind of a trajectory which can be considered as smooth, and the time intervals between them is t1, and it would go up to t2. So it is going from the variable qt, which is going from t1 to t2. So what will happen is that if I take the general Lagrangian, so that would be S, and I would put up the braces, so it would be Q, and then it would become this t. And then what I am going to do is that this s is the Lagrangian. So I will take the integral starting from t1 and it will go up to t2. And the Lagrangian L would be what? The q. And then I will take the q dot, that is the derivative part. And I will take the differential time, that is dt. Right? So this is basically what is the Lagrangian which is considered. So I'm taking S as a system, followed by the integral of t1 to t2. And remember, this is a dot over there so that you don't miss on the integral. So in this formula, what is going to happen is this part, L, then I take q comma q dot. This one is the Lagrangian. So this would be considered as the Lagrangian, this one. Remember, again, don't miss the dot over here so that you can understand. So this one is basically the Lagrangian which is considered. Okay. Okay, fine. Now, say for example, if I take this LQQ dot, what we can tell from here? What we can tell from here is this would be equal to, let me put it as E, and I will tell it as kinetic energy, right? And then I will put a brace and I will take again the Q, right? And there's a dot over here. And it will be minus of what? Because this is a Lagrangian. So it would be obviously the potential energy, which will be POT. And this would again be equal to what? Can you tell me? This is simple. This would be m upon 2 followed by the square of this q dot, the differential, the derivative, right? Followed by minus of vq. Minus of vq. So what I did right now is that I have taken this as the Lagrangian, right? I've taken SQT is this one is the Lagrangian. And in this formula, the Lagrangian is kinetic minus the potential energy, which becomes equal to this. Okay. Now, what you see from here is that the integral which I get is basically an ordinary function, L of two variables. That means if I, just a second, yeah. So if I take the Q and if I take the Q dot, this Q and Q dot, they are actually evaluated as what? As QT. And this is evaluated as what? This one is evaluated as dq within bracket t and whole divided by what? Dt. Simple. Like, let me write it fresh. Dt. Right? So this is evaluated as dq by dt. Okay. So this is for the specific trajectory. Which is the specific trajectory? This one, qt. Okay, this is the specific trajectory. This one. This is for the specific trajectory qt. For time t, obviously the time is t. Okay. So this is quite understood. Now let us consider, say for example, okay, let us consider the set of all possible trajectories. For example, if I take up qt, right? If I take up qt, I will take up all the possible trajectories qt, which begins at the same value q1, and it begins at time t1. So we are considering the set of all possible trajectories. So what happens is that this S is actually the functional of the trajectory qt. This S is basically the functional of the trajectory qt. That means the entire history, this one, which I have just drawn earlier, this entire history of the trajectory is taken into consideration. So this one, this entire history is taken into consideration. So the history of its motion rather than a specific value. So the entire history, the entire trajectory is taken into variable, because S is a functional of the entire trajectory QT. So S is basically the functional of the entire trajectory QT. So far, so good. So from here, what we see is that now we consider all possible trajectories of QT, which begins at the same value Q1, and at time T1, it ends at the value T2. So what happens is that the least action principle states that the trajectory, which is the lowest action integral, that means S followed by this Q, followed by this T. This is actually the least action principle states that the trajectory which is the lowest action integral, this has got the lowest action integral. Among this is the set is the classical trajectory, and it happens to obey the classical equations of Newton's law. So this would actually obey the classical laws of classical Newton's law. Now, in order to see this, in order to find out this, first of all, what we need to go over is that we need to see how this works. So let us take any test trajectory. Okay, let us move fresh. So I will take a kind of a test trajectory, and I will mention, say, for example, just a second, let me see if I can do this one. I will take this test trajectory as Q followed by a bar and followed by the bracket T. So this is my test trajectory. I will take this one. I will take this test trajectory, and I will consider its infinitesimal variation. What is the infinitesimal variations? I will consider Q of T, and I will take this as equal to Q, this one on the top I am putting a bar so that you can understand this is different, QT plus, for this infinitesimal change, I will take this variable del or delta, whatever the way you call, of Q of T. So what I'm doing is that I'm taking a test trajectory. This is the test trajectory which I'm taking, this one, this part. And for a very infinitesimal small change, I'm putting this one. So if the trajectory, this one, QT, happens to minimize the action functional, or even say, for example, it is any other kind of a trajectory, then the first variation of the action will be vanish. That means what? That means del of S will be equal to 0 because it will vanish. So this del of S will be equal to 0. So if I calculate this del of S, that is the first variation, what it would look into? What it would look into? Let us see. So we calculate this one, del of S will be equal to what? Definitely it will take the same integral. It would start from T1, it would go up to T2, and it will take the infinitesimal small change of the Lagrangian followed by the differential time. So it will take this one from T1 to T2, and it will take an infinitesimal small change followed by the differential time. So this is the test one, and I have made a small change. I'm repeating it, and the action principle is 0. So I have done a small, the Lagrangian up to dt. Okay. So what happens if I take this one, this infinitesimal small del L, right? That means it is what? For time t. So let me write it for you so that it becomes clear. This is for time t. This is for time t, which will be equal to what? Definitely, I will get the, I will get what? I will get the partial derivative of L, with respect to the partial derivative of Q, that is the particle, times what? The infinitesimal change. Obviously, the partial derivative has to be followed by the infinitesimal small change, that is this one q within braces t, and this should add up with what? This should add up with the Lagrangian. Which Lagrangian? Which has got this derivative. That means if I take the partial of L, this one, this same partial I am taking. But now what I will do, I will take the Q followed by the dot. This followed by the dot, because this one is now being differentiated with this. So I will take this one Q dot, right? And it will be what? Times this differential d by dt. Obviously I have to take the time. So first I differentiated with this one first, then I differentiated with this one which has got a dot, a d by dt, and then it is followed by what? The differential small change, that is, also sorry, this would be del q followed by t. So this equation, I hope it is clear. This is absolutely clear. The uncertainty principle is the relativistic case. Yes, Sumit, you have rightly told, but yes, I will explain on that. That's a very good point Sumit has raised, that uncertainty principle is the relativistic case here. But we are coming to the uncertainty principle one by one. Let me show you how things happen. But thank you very much for the comment that you have put up. It shows that you are watching the live streaming very closely. So thank you very much for that. Okay, so we get up to this. Now, what we can sell is that the derivatives of L, this derivative, the derivative of L, this is evaluated for what? This is evaluated for Q, which will be equal to the test particle. And what is the test particle? This has got a bar over it followed by T, right? It has got a bar over it followed by T. And it will be also, the derivative will be another one, which is Q, differentiated. So this will be dot followed by what I'm going to differentiate. I'm going to differentiate d followed by this q, the test particle, with respect to what? Time. So this would be respect to time, whole divided by dt, obviously. Otherwise, how will it differentiate? So this part becomes clear, right? So the derivatives of L are evaluated in terms of this one first, and then it is differentiated in terms of this one, this part. Okay, so from here what we can get, I mean to say, if I substitute and do the integration, let me show you how it evolves into. So if I do the differential, what will have? First of all, I'm going to take the infinitesimal small, so I will type as ds, which will be equal to what? Simple, the integral of t1, I hope this is clearly visible, T2, I know that it is a little bit cumbersome, and then I have to put a brick bracket. Why? Because I have to take the partial of L, and then I have to take the partial of Q, followed by the partial of Q in terms of T. This is one term. Then it should be added with what? You can yourself look into it. This should be added with this one, right? This one followed by this one, this part, del L, and then del Q. So let me write it. It is quite simple, a very simple integration, nothing to worry about. So we write it as the del of L followed by del of Q dot, right? Remember, these are partials. This is the del, this is the partial, multiplied by d by dt, obviously with respect to time, d by dt, and it will be what? A function of time. So I put it t, and then I close the braces followed by dt. So let me show it closing, zooming out a little bit. So this is how we started. So this is how we started. So we started with this one, and then we got the test variable this, then we integrated this, and we know that this is with respect to time. We got into this one. We got into this one. Okay. So from here, what do we get? So if I integrate the second term part by the parts, I'm just skipping the step, making a little bit quicker, because again, writing it would take a long time. Sorry. So this would be, okay, let me show this to you. Yeah. So this would be equal to, what? This would be equal to the integral of T1 and T2, followed by the del of Qt, followed by times, then I put again a brace. So what I will do, I will differentiate the partial of L followed by the partial of Q, minus. Why I'm putting it a minus, you can obviously guess, because I'm now putting up the d by dt part. I will put up the d by dt part, and then I will again differentiate the Lagrangian, followed by the partial of q dot. This is a dot, and then I will close the braces and I will put a plus and then remove my screen a little bit, and then I will put, this is the one, del q times del partial of L, and in the denominator it will be what? Same this thing, same this thing, partial of q dot. And remember, this is something which has got the time interval. That means I can write this one as T2 to T1. Clear up till now? So this is how we are going ahead. Now, from here, what we can find out is this. Now, here we know that due to the initial and final conditions, we know that there is an initial condition and final condition. So Q of T1, this one, and Q of T2, this one, Q of T1 will be equal to Q1, and Q of T2 will be equal to Q2. Right? We know that the initial and the final condition matches up. That means from here, what we can also get is this one. Let me put just this one and this one. So what I can write it cleanly is that the del of Qt1 will be equal to del of Qt2. Simple. Is the braces, and then we can put it as 0 because it is a killing boundary term, right? This is a killing boundary term which has got in equation 5. So what we get from here, finally, where do we arrive? What we get from here is this one. Okay, let me put this part. So we get what is that this S followed by this Q will be equal to what? The integral of del Q times, can I put a big brace because I have to take the Lagrangian of L followed by the Lagrangian of Q, minus d by dt, and then I take the partial of L followed by the partial of Q dot, and I close the braces, dt. Okay. So here what happens is that we want this variation to vanish. That means for any kind of a, I would say, let me push it further. Okay, so for any kind of a, I would say, del Q of T, right? The only way which it can happen is that it vanishes the term. So how does it vanish? This is how it does. So I can put the partial of L followed by the partial of Q minus, obviously it would be d by dt, and again I would take the partial of L followed by the partial of Q dot, which is equal to 0. So from here, what we can get is the Lagrangian of L. So we can get from here the Lagrangian of L, which is equal to 1 by 2 m q dot squared minus vq, obviously. And from here, what we get, you see, this part, if I consider this entire part, this is basically the equation of motion. This is actually the equation of motion. So what we have seen from here, particularly, that what we have derived from here is that the Lagrangian actually somehow gets reduced further to this one. And this we can show in the next part of our lesson, is that how this is equal to the equation of motion. So let me again add it. This particular part, which I'm right now, which is displayed on the screen, this is nothing but, this is basically, I will tell you, we can further derive into this. This is actually the Lagrangian for a non-relativistic particle with mass m and potential energy Vq. So the first term, I can say this part, this one is actually what is called the kinetic energy of the particle. So in classical mechanics, the kinetic energy is half mv square, where v is the velocity, because here the Lagrangian uses a generalized coordinates q, so you can express the kinetic energy as half mq square. And what is this vq term? What is this vq term? This vq is basically the momentum. I would say the terms that represents the potential energy, that is the kinetic and the potential, which depends on the position q. Again, potential energy associated with the forces acting on which the particle can be expressed. So in this case, of a particle of a gravitational field, Vq might be again mgh, where the height above is a reference point and g is considered to be the gravitational acceleration due to gravity. So what you can see right now, L equals to half mq dot square minus Vq, is basically the Lagrangian for a non-relativistic particle. The first term is the kinetic energy of the particle, the second term is the potential energy of the particle, and the Lagrangian is basically the function of the particle's position q and its velocity q dot. So from here, what we get is that because the term corresponds to the kinetic energy, which is very, very important of the particle, sorry, and because in classical mechanics, the kinetic energy of a particle is half mv square, and this Lagrangian actually generalized to a much bigger and broader coordinate. So that is how. So we will take a pause in today's lesson, and I will continue tomorrow also with few more equations. This time I can assure you the equations will be much cleaner and much clearer, so that I can show you to you how things are. And from here we will then go into Euler-Lagrangian equation, and then I am going to explain you that the equations of motion, the Newton's second law, how does it come from and why it is very important. Once you understand the Lagrangian, the Euler-Lagrange, and then from here we will move into what is called the Lagrangian density. So that is all for today's lesson. I think you have really liked it. So we will actually start tomorrow from equations of motion, Newton's second law, and how it can be derived from the Lagrangian, why it is derived from the Lagrangian, most importantly, and how these things are important. So stay tuned for tomorrow's yet another lesson on quantum field theory. We'll see you soon, and goodbye.